and let's move on to our next presenter, Matthew Grohotolski. So Matthew, feel free to share your screen, and you are going to tell us about a real-life PokéDex, which I'm intrigued by.
Thank you very much, and good afternoon, everyone. My name is Matt, and the project that I'm presenting on today is called PIKA. So it stands for Pokemon Interpreter Using Keras and Acceleration. And we'll get right into it. We'll go over a little bit of an overview here of what we'll be covering. So the inspiration behind the project, some existing problems that that lie in this field. We'll go into data pre-processing, and then training and testing the models that were used. And then finally, we'll go into a demonstration of the application that I made. So some inspirations behind the project is Pokemon is one of the most recognizable games around. It's originally a Japanese-made video game, and recently with like things like Pokemon Go hitting the scene, a lot more people have been exposed to Pokemon, so it's a growing interest among fans, and it remains popular to this day. So some existing problems are the optimal classification model for identifying Pokemon. Documentation on prior works are very limited, and previous works weren't trained on a variety of images. Also, the ability to detect on an iOS smartphone. So one of the previous works that I found only works on Android devices, and a large amount of users nowadays actually have iOS devices instead. So these are just some of the problems that I wanted to try and resolve. So we'll go over some basics about image classifications for those of you who aren't familiar. So it's very easy for humans to do, but not so much for computers. It takes a large amount of compute power to compute something like this based on an image. So it's very popular nowadays with powerful computers, cameras, anything in video analysis or the medical fields especially. And it's something that is hard to adapt to smartphones. So basically, a computer can analyze an image and identify the class or label under a probability. So it'll give you give it an image, and it'll give out some labels along with percentages for accuracy. And here's a good example of how an image classifier might work. So on the right hand side, you can see an image of a cat, and then on the right of that, you can see uh, part of the computer views, what the computer can see. So the computer's view is actually a 3D array of numbers. So we could say that the cat is 248 pixels wide and 400 pixels tall. Then each pixel is actually comprised of 3 color channels for red, green, and blue. So that'll give us our 3D matrix of numbers, and that gives us a lot of data to classify the image. So each pixel can be value from 0 to 255 in each respective category, red, green, and blue. So that's a little bit of how the computer can see an image, and then we'll go on to how it can learn in future slides here. So some image classification challenges that we could run into along the way are like viewpoint variation. So what happens if an image is turned or distorted? Also scale variations. So in one image, Pokemon might be very small, or in another, it might be very blown up or closer to the frame in the camera. Uh, a third could be deformation. So some images might not look the same. Pokemon might be moving in different ways, and the program would have to account for that. And then lastly, occlusion. So what happens if the object is behind something in the frame, say like it's occluded by a wall or something like that. And there's actually some solutions to these problems. So I've used something called an image data generator, and what that does is it actually randomizes some of the image to give us more data to pull from for training. So the first example is image normalization. So this just transforms our 0 to 255 values to a scale of 1 to or 0 to 1. And the second would be shearing. So this can be seen by cutting off different sections of an image. So this gives us more images to work from when we train our model. Same goes for zooming, just gives us more data to pull from. So we can zoom in and out from 0% to 20%, and that just helps to better generalize the model. And also with the horizontal flip, so flipping an image will also give us more data. So we'll go into the data that was used here for the project. So I decided to go with the first 25 Pokemon, and I figured that would be a good baseline. There's I think over 900 Pokemon now, so it would be a little extreme to add all of them. So I first found a Bing data set on Kaggle.com and found that the data set wasn't generalized enough. It actually didn't contain quite enough images. So I had to come up with a creative solution to add more images to this data set. So I actually ended up making a Google scraper to download images automatically. So I ended up going with a combination of both data sets then. So the one that I found on Kaggle and then also the Google scraper comprised data set. So this gave me I think over 100 images for each Pokemon. I think I actually had about 200 before pruning the junk images. So I deleted many images that weren't helpful, so that just didn't associate with the given Pokemon. And then I used a JPEG format. So this just has a depth of 3, so like the RG for the RGB channels. And I'll discuss a little bit more about the Google Scraper method that I used. So this pretty much does a Google search and scrolls down the page with a little bit of a timer delay, and then it downloads each image on the Google Images result. So in this example, I just downloaded the first 100 photos. So I would search for the Pokemon's name and then a space followed by Pokemon, and I found that that yielded pretty good results for images of the Pokemon. And then I also added another 100 images of some Pokemon plushies to give the data set even more generalizability. So here's a little bit of a flow chart for how the data set creation works. So we have the Google image scrape on the left and a remove junk images after that. And we can see here the Bing image scrape is added into there. So I selectively added only the images that apply to that Pokemon, and that yielded the final data set, which was also republished back to Kaggle in case anybody wanted to use it in the future. And we'll go over some of the models that were used here now. So the first model that was utilized is called AlexNet, and this is comprised of 8 total layers. So there's 5 convolutional layers, which do most of the learning for the model, and then there's 3 fully connected layers, which kind of try and condense that learning down to an output result. So you can see some of the parameters that I used here for the model. And at the bottom here is a good layout of how the model would look. So we would give the model an input, so an image of 224 by 224, and that would get passed through several convolutional layers to do the learning. And then at the end here, finally, it's outputted as a value. In this example, it's 0 to 999, but I used a value of 0 to 24, so it would give 25 outputs for each of the 25 Pokemon. And we can see that the AlexNet actually resulted in a pretty good score. We got about 74% accuracy here, and I wanted to train it for a long amount of epochs just to get a good consistent base to see how the training would fare over a long amount of time. So this actually took multiple hours to complete, even with my graphics card. It took quite a long time to get fully trained, and yeah, we got 74% over all of that time. So definitely left some space to be improved, which brings us to our next model. It's called the VGG16 model. So it just comprised of different layers than the AlexNet. So VGG16 is a convolutional neural network, or a CNN, that's 16 layers deep. So it's actually deeper than the AlexNet. So I wanted to try some different things out to see if we could improve the training rate and the accuracy scores. So you can see on the model down in the bottom right, we can see the image input followed by these 16 layers. So here it's using a lot more convolutional layers to do more learning, and then it's finally outputted to a 0 to 999 value. But again, in the program, it would be only 25 values. And for some reason, this always seemed to give a bad result. So I could only ever get it up to about 7%, and I tried various different methods and models for the VGG16, but none of them could really figure out how to learn quite right. And then that brings us on to the final model type. So this is the VGG16 with ImageNet. So I actually discovered that by using this ImageNet as a background, it would greatly improve the accuracy scores. So for anyone that doesn't know, ImageNet is a very popular pre-trained neural network. It hosts over 15 million labeled high resolution images and roughly 22,000 categories from those. So this could be anything from boats to planes to people and cars. And it gives a common set of images to benchmark models and algorithms. So for the VGG16 with ImageNet, it utilizes all of the weights and pre-learned details into the top layer of the VGG16 model, and it's set so that it's not trainable, so that when I'm training for Pokemon, it's not rewriting over the ImageNet data and losing all of that memory that it has. So this greatly helped the VGG16 model to classify the Pokemon, and it gave it a very solid foundation. It also helped to train the model quicker. So whereas before I had to use about 300 epochs to get the full effect, this one got it done in about 30 to 50 epochs. Now I still did use the 300 epochs just to see as a baseline to see if it would improve over that time, but we can see here in a little bit that it didn't. And here's a little bit of code that goes along with the VGG16 with ImageNet. Um, we can see just at the bottom here, like setting the layer to be non-trainable. So without this, I actually test it and it kind of overwrote some of the ImageNet data and didn't give as good as scores. But when we use that as the background, that's really the key to getting these good numbers here. So when training over the 300 epochs, we can see we ended up with an accuracy of 95%, and that's definitely far outdoes the previous two models. The best that we got with AlexNet was about 74%. So definitely a huge improvement here when using this ImageNet as a background for training. And I also conducted some exploratory data analysis just to test out the model and see how it fares when testing against images. So here's some images. You can see for each title of the image, it has the prediction on the left and then the actual factual, uh, like what the Pokemon is named on the right hand side. And it does pretty good here. We can see that it gets about 96% accuracy in this test, with the only thing failing is this bird type Pokemon, because it's just hard to classify. And then what I use to make the app here is something called Kivy. So it's a cross-platform Python framework and can be deployed on a number of operating systems. So all the mainstream operating systems such as Windows, Mac, and Linux, and then also the smartphone operating systems like iOS and Android. It supports GPU, which is like graphics card acceleration, and it allowed me to create a very natural user interface. I actually ended up finding an additional add-on to Kivy called Kivy MD, and pretty much what that is a more modern layout for Kivy. It uses Google's material design layout, so it ends up looking a lot more natural than just using the base Kivy framework. And then I also made a GitHub repository along with the Kaggle dataset. So if anybody's interested in the code, like the full code behind the project, or even the dataset, I can shoot you guys the links after the presentation here. And now we'll be moving on to the demonstration. So let me just get this set up real quick. And I'll share the app screen. So the main app screen here, you can see it just has it's just like a basic Pokédex. It has all of the 25 Pokemon here. You can scroll through the list. So what's interesting here is I actually have the camera on, so we can scan in some Pokemon and see how the classification does. So we have a Pikachu here that we can scan, and we can see that the app actually does identify it as a Pikachu Pokemon and gives us some details here. And I have some additional ones. So we have a Beedrill, it's called. And there we can see the app detects it and displays that. We have this guy, this is a Squirtle. There we can see it. It brings it up right away and does a really good job of classifying. And then lastly, we have this Pokemon. And yep, we can see it does a really good job of being very accurate here. So lastly, the last thing I want to try is just scanning myself just to see what the app thinks I am. So it looks like I'm classified as a Venusaur. And yeah, that's my presentation. That's the app that I created, and I hope everybody enjoyed it. And that brings us on to the questions, if anybody has any.
Great, thank you for that presentation, Matt. That was a lot of fun, and yeah, very cool. So yeah, we have time for maybe one question from the audience.
Does it ever come back that it doesn't know? Like you show it a picture and it won't give you an answer?
So sometimes it'll actually give wrong answers if it can't fully understand the image. Um, it's very common if you try and like manipulate the Pokemon that you're trying to show it, or back up too far or something where it's out of frame and can't really understand the Pokemon. Sometimes it'll use like data around, so like the background, for instance, and it'll use that for its calculations sometimes. So there is some varying results that it can give you back, but it'll never not give you a result. It'll always try and at least guess the Pokemon that you're trying to show it.
Great. All right. So yeah, thank you very much, Matthew. And I like that you have the link there to share with folks who want to explore your code a little bit further. Great. So let's give Matt a hand.